Assalamualaikum. Hi again. VEKU 2333 Electrical Circuit 2. In the chapter Frequency Response, today we're going to discuss about series resonance. Series resonance occurs when any system has a complex conjugate pair of poles in any act that has at least one inductor and one capacitor. The definition of resonance is a condition in an RLC circuit in which the capacitive Xc and inductive reactance XL are equal in magnitude, resulting in a purely resistive impedance R. It's useful for constructing filters. Transfer functions can be highly frequency selective, and in many applications it can be used, such as selecting the desired stations in radio and TV receivers. This is an example of a series resonance circuit. It has a supply voltage Vm with an angle. It has R, j omega L coming from the inductance, and 1 over j omega C coming from the capacitance. Now the transfer function H omega is equals to Vs over I, and that is its impedance Z. And that is equals to R plus j omega L minus j 1 over j omega C. And if we collect the j together, the imaginary part will become omega L minus 1 over omega C. Now resonance results when the imaginary part of the transfer function is equal to 0. Looking at the imaginary part, omega L minus 1 over omega C, we rearrange that, and we will have a frequency of both L and C, omega naught, which is equal to 1 over square root LC. Now that is the value of omega that satisfies this condition. We call it resonant frequency, omega naught. And we know that omega naught is equals to 2 pi f0. So our f0 in hertz is 1 over 2 pi LC. The frequency response of the resonance circuit for the current is I, or magnitude of I, is equals to Vm. So where is Vm coming from? It's from Vs, its magnitude, divided by the impedance, square root of R squared plus omega L minus 1 over omega C squared. This in turn will result in a graph with a bandwidth of between omega 1 and omega 2. Now the peak is at omega 0. At that point of time, the average power dissipated by the RLC circuit, we know this as P of omega, it's half of I squared R. And the highest power, as said before, is this highest power dissipated occurs at resonance when I is equal to Vm over R. Now replace that I with Vm over R, we'll get the power at omega naught is equal to half of Vm squared over R. What are the features of series resonance? The impedance is purely resistive, or Z equals to R, as LC series combination acts like a short circuit. The supply voltage Vs and the current I are in phase, so cosine of theta is equal to 1. The magnitude of the transfer function H omega equals to Z omega is minimum, and the inductor voltage and capacitor voltage can be much more than the source voltage. At certain frequencies, omega equals to omega 1, omega 2, the dissipated power is half the maximum value, that is, half of Vm over square root 2 squared divided by R, or Vm squared divided by 4R. Omega 1 and omega 2 are called the half power frequencies. The half power frequencies can be obtained by setting Z impedance equal to square root 2 over R. And we'll see that omega 1 and omega 2 are as shown, and omega naught is the square root of omega 1 multiplied with omega 2. For high quality circuits, Q greater than 10, we have omega 1 and omega 2, which is separated, which separates the bandwidth, omega 2 minus omega 1. And as shown in the previous graph, thus the quality factor is the peak energy stored in the circuit divided by energy dissipated by the circuit in one period at resonance, or omega naught L over R, or 1 over omega naught RC. It relates the maximum peak energy stored to the energy dissipated in the circuit per cycle of oscillation. In the series RLC circuit, we have omega naught L over R and 1 over omega naught RC. The relationship between B, Q, and omega naught is as shown, in which B is equal to omega naught over Q, or omega naught squared RC. And the quality factor is the ratio of its resonant frequency to its bandwidth. If the bandwidth is narrow, the quality factor of the resonant circuit is high. Now, if the band of frequencies is wide, the quality factor must be low. Q equals to omega naught over B. This results in the graph shown. Q1 is the one with the least sense selectivity, and Q2 medium, and Q3 has the greatest selectivity. Note that B3 is the smallest bandwidth with the highest Q, and B1 is the largest bandwidth with lower Q. Selectivity is actually the sharpness of resonance. Now let's try an exercise for series resonance. Series RLC network has R, L, and C as shown. Now try to find the resonant frequency, omega naught and F naught, and find the bandwidth and see the quality factor. So plug in the equations, you get omega naught 141.421 kiloradians per second, and you get frequency F naught is 22.51 kilohertz. Bandwidth B is equals to 10 kiloradians per second, and Q is equals to 14.142.